Well, hello, chemistry students. Let's get started with some chemistry today. We are going to talk about the mole. No, not the furry creature that lives in the holes in the ground. We're going to talk about the all-important mole that we use in chemistry. So let's get started. Turn to your study guide to lesson 8, the mole, and we will get moving along. All right, I'm going to put up our friendly mole here. Come back to it in just a minute. All right, so you should be turned to lesson 8 in your study guides. We're actually going to divide lesson 8 into 2 videos. So this is the first of the 2, and let's just kind of dive in right into what the mole is and define it a little bit, get it to understand about what the mole is, and then we'll use it for some calculations. So I'm going to use the board today to help us with that. So first of all, I want you to think about this. If I use the term dozen, what comes to your mind? Most people, the number 12, or 12 donuts, 12 eggs, maybe 12 cookies, but usually the dozen has a value of 12 associated with it. Okay, so I'm going to write that down actually. Grab a marker. 1 dozen equal to 12, and really it's 12 of anything. Like I said, 12 eggs, 12 donuts, 12 cars, whatever, anything that is the value of 12 is a dozen, okay? Well, we can think of the mole in the same way. The mole is a value. Now, the value of a mole is much larger than 12, okay? It's an incredibly large number. It is, ready? 6.02 times 10 to the 23rd. Yes, that is right. To the 23rd power of anything. So we could theoretically, but not realistically, have a mole of donuts, right? Now, yes, that is a heck of a lot of donuts. I couldn't even imagine that number of donuts, okay? So in fact, let's do this. Let's write out this number. Let's come over here and do that. So 602. Okay. Now, how many more zeros? We should have 21 additional zeros, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Still not done. Whew. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and finally 21 zeros. Okay, look at that. That is huge. Let's put in some commas to help us out with that. So there's a comma. I should have comma, 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 and comma. Oh my gosh, that is one ginormous number, and I mean ginormous. Right? What is this number? I don't even know. It's like 6 billions or something like that. It's just huge. Okay. So, other than the fact that this is the exact amount of moolah, money, in my current bank account, of course, when else would we use this large number? I mean, it's so big. I mean, I can't even imagine going to the bakery and say, hey, can I have a mole of donuts? Holy macro, okay? That's just ridiculous, okay? I can't even count to this number, all right? Not even in a lifetime could I count up to a mole of anything, all right? Even on day 1, if I started counting pennies, if I wanted a mole of pennies, right? It's a lot of pennies. it would be like, okay, here we go. Day one of my life, 1 penny, 2 penny, 3 penny, 4 penny, 5 penny. Okay, I could spend my entire life and never ever even coming close to counting to this number. Okay, so why do we even bother using such a large number or using the mole in general? Well, you got to think that in everyday practical terms, we don't. Okay, I'm not going to ask for a mole of donuts or a mole of eggs or a mole of pencils or a mole of pennies. Okay, I'm not going to do that. Okay, but you got to think in terms of chemistry. Why would we use the mole, which such a large value number in chemistry? Okay, think about it. What are we dealing with? Well, we're dealing with very small particles, elements, atoms, protons, electrons, neutrons, and even smaller. Now, these particles are so small that, again, we cannot see them with our eyes. We're barely even seeing them with special types of scanning electron microscopes, just the surface of these atoms, let alone ever seeing a proton, neutron, and electron. Okay? So if I'm actually going to deal with a certain amount of atoms or a quantity of atoms, I'm not going to start seeing them, visibly seeing that quantity of atoms until I get up to a mole, okay, up into this frame. Let me give you an example, okay? So, oops. I have here a rod of copper atoms, okay? See that rod, okay? All right. Now, I can fit this rod in the palm of my hand, right? So how many atoms are sitting in the palm of my hand of copper? Well, it turns out that there is exactly 1 mole of copper atoms in this rod. 1 mole. There are 6.02 times 10 to the 23rd atoms of copper right here in this rod, okay? Now that is a lot of atoms, but remember, those atoms are so tiny that it's gonna take a lot of them to be able to have them a visible amount in the palm of my hands. So in terms of chemistry, chemists use the mole so that we can know the amount of atoms or other particles that are so small that we're dealing with, that we're playing with and using, okay? Let me give you another example here. This is aluminum, it's the element aluminum. Here's another rod shaped, okay? This itself is also a mole of aluminum atoms, 1 mole of them, okay? Exactly 1 mole, okay? 1 mole, 6.02 times 10 to the 23rd aluminum atoms. Now compare that to the copper, okay? Different sizes, okay? Now why might that be? Why they both have the exact same number of atoms, right? This has a mole of atoms, this is a mole of atoms, 6.02 times 10 to the 23rd atoms of copper, and 6.02 times 10 to the 23rd atoms of aluminum. Why? Well, first of all, they're going to have different volumes, right? Different atoms, different volume sizes, right? So that's going to account for a little bit difference there, as you can see. Also, they have different masses, right? Right? Different masses. And that might have a bearing on this, okay? What about another one? What else do I have? I have mole of iron, okay? Mole of iron is fairly comparable to a mole of copper, okay? very close, but still, nevertheless, this is 6.02 times 10 to the 23rd iron atoms, okay? Now, how do I really know this, right? I mean, I just got done talking about the fact that there's no way that I could count a mole of pennies in a lifetime. How am I going to count a mole of atoms? I mean, I'm going to take a bag of copper atoms, right? Take a bag of copper atoms and then start counting 1 copper atom, 2 copper atom, 3. Yeah, that's ridiculous, okay? I can't do that, all right? It's not going to work. But what if I knew how much a mole of copper atoms weighed? Okay, if I took this mole of copper atoms, it's going to have a certain amount of mass to it. And if I knew what that mass was, then I know how much weight that 1 mole of copper would have, right? The same thing with aluminum, right? If I had a mole of aluminum atoms, put it on a balance, I then would know the weight it would take to have a mole of aluminum, okay? So that's what we do. Now, how we got through all of that is beyond this discussion of the class, okay? But what we're gonna do is just focus on that understanding right now, okay? So how do I know if I look at an element, say carbon, for instance, how do I know right away what is the mass of carbon that's equal to 1 mole of carbon atoms? Okay, well, the thing is I can get that from the periodic table, okay? So all of you should have a periodic table. Let me put these down. Grab my periodic table. I've given you a periodic table, so you can use the one I've given you, or maybe you've printed out another one, that's fine either way. But the periodic table holds the clue to this, all right? Now, we've already talked about that each element is in a box, right, in the periodic table. And in that box, not only is the symbol of the atom, but also the atomic number, which is the number of protons, and then it has the mass number. And the atomic mass, okay? And the atomic mass is in AMUs, or units of atomic mass units. We've discussed that, okay? So if you look, we're using copper, let's talk about copper, okay? So let's look at our periodic table. And if I glance at the periodic table, I will notice where copper is right here on the periodic table. And you see its atomic number 29 right there, all right? But the mass is what? 63.55, okay? 63.55 atomic mass units. But if I take that value, that mass value, and I weigh that out in grams, it has to be in grams, okay? That's important. So if I weigh out that value, let me erase this board and then write that value up here. Okay. I'm going to erase this value mole here for a minute. So if I write, again, what was it? 63.55 grams, okay? I weigh that out of copper, okay? So remember my copper, my rod of copper, right? And it turns out that this rod of copper is 63.55 grams, okay? It turns out that this value of mass for copper is equal to the 1 mole, okay? It's awesome. Every time I weigh out 63.55 grams of copper, I will have a mole of copper atoms. It's that simple, okay? I can get it from the periodic table, all right? Let's look at aluminum. Remember we showed you aluminum. So let's look at aluminum. Well, if you look at your periodic table, right? Go to your periodic table. Aluminum is sitting right there. Okay. So atomic number is 13, but what is the mass? Okay. Well, the mass of aluminum is 26.98 grams. Okay. Well, in other words, if I weigh 26.98 grams of aluminum based on my periodic table, it will equal 1 mole of aluminum atoms. Okay, so guess what mass this is? You guessed it. Okay, it's 26.98 grams. I put that on a balance, I have a mole of aluminum atoms. Okay, it's that simple. Let's look at another one. Find carbon on your periodic table. Okay, look at it. All right, atomic number of what? 6? Good. All right, what is the atomic mass? Okay, according to this, is 12.01 atomic mass units. So if I change that unit to a gram and weigh out 12.01, remember it has to be in grams. If I weigh out 12.01 grams of carbon, it will equal 1 mole of carbon atoms. 1 mole. Okay? It's that easy. Just use your periodic table, take the atomic mass, change the unit from AMUs to grams, and that amount of mass of that element is equal to 1 mole. Now we have defined this value for these elements. We call this the molar mass. Right? And it's there in your study guide. The definition of molar mass is essentially the number of grams of an element that's equal to 1 mole. Okay? The number of grams for an element that's equal to 1 mole is the molar mass. All right? So this is the molar mass of copper, molar mass of aluminum, and the molar mass of carbon. Right? Awesome. Let's do another one. All right. Let's look at our periodic table, and everyone, let's find fluorine. Okay. Want to find fluorine? I'm gonna erase all of that. All right. Fluorine. I found it. What is the molar mass of fluorine? It should be 19.00 grams is equal to 1 mole. Okay? So if I take a bottle of fluorine and I weigh out 19 grams of fluorine, I will get 1 mole. Okay? That's it. It's simple. That's it. Now, I do want to mention one important thing. As far as dealing with sig figs and everything, we're going to go out to two decimal places in our molar masses. Okay, 2 decimal places. So on the periodic table, if they go out to multiple decimal places beyond 2, go ahead and round to 2 decimal places. Okay, that's what we want. Yeah, I mean that's it on that idea. Okay, so if you look at, for instance, pretty much everything on this periodic table that I've given you is already rounded to 2 decimal places. Okay, and that's going to be the standard for the AP test and the IB exam. Is you're going to round out to 2 decimal places. Okay. All right. Now another way of representing the molar mass is exactly as it says, 19.00 grams of fluorine per 1 mole. Okay, so these two are written are written identical for the molar mass, okay? Either way you can represent that. Let's do one more, for example. Let's do, I don't know, chromium, okay? Chromium it has a molar mass. If you look at chromium, it's element 24. So chromium has a molar mass of 52.0 grams, equals to 1 mole, or we can rewrite that as 52.00 grams per mole, okay? So either way, it can be represented, the molar mass, in that terms, okay? This way, it's more of a conversion factor setup, and this way, it's more of a traditional unit setup, okay? So depending on how you're using the molar mass, maybe how you write it, okay? That's it, that's the molar mass. For an element, that is. What about for a compound? How would we find the molar mass for a compound? Okay, so in your study guides, we have a few examples of finding the molar mass for a particular compound. And if you look, I think example 1 is water. So let's do that. The molar mass for a compound is not hard. You just have to do a little bit more calculation, okay? So water has the formula, chemical formula of H2O. So it's made up of 2 hydrogens and 1 oxygen, right? So if you look and break this down, so hydrogen, what is the molar mass of hydrogen? Well, if I round it to 2 decimal places, it should be 1.01 grams per mole, okay? But I have 2 hydrogens in my formula, so I technically have to multiply this by 2, okay? And that will give me 2.02 grams per mole, okay? And in this particular case, because of the 2 hydrogens. Oxygen, if you look at oxygen on the periodic table, you will find to 2 decimal places that it's 16 grams per mole. We only have 1 oxygen, so multiplying by 1 is just 16.00 grams per mole, okay? So that's the essential molar mass of the individual atoms that make up water. So now all we have to do is add. We're going to add these 2 values, so that makes it 18.02 grams per mole of water, okay? So this is the molar mass of water, 18.02 grams per mole, all right? Or if you're using it in more of the conversion factor form, it's 18.02 grams per 1 mole of water, okay? And there you go, your molar mass of water. Again, all I did was take the individual molar masses and multiplied them by the ratio subscripts and then added, and voila, I have it, okay? By the way, abbreviation for mole, so MOL is mole, right? The abbreviation is just MOL. We just dropped the E. There's the abbreviation for mole, okay? Super easy, all right? Good, let's try another one, all right? There's water. What's the other one? You have, oh, yes, rust, iron oxide, okay? So Fe2, O3, all right? So again, we break it down into iron and oxygen, our 2 elements that are in our formula. The molar mass of iron, if you look at the periodic table, it's 55.85 grams per mole, okay? And then I'm going to multiply that by 2 because I have 2 irons, and that's going to give me 111.70, okay? And then for oxygen, again, with 16.00 grams per mole, but I have 3 of them, So I multiply that by 3, and I have 48.00 grams per mole. Okay, so that's where I currently am at. Molar mass of iron multiplied by 2, molar mass of oxygen multiplied by 3. Now I just need to add these two, right? So I have 159.70 grams per mole, and I add them up, okay? Or 159.70 grams is equal to 1 mole of iron oxide, okay? So there's my molar mass, okay? Pretty easy. Not too bad, hopefully. All right, there's what, one more in your study guide there. Let's have you work that out. Why don't you go ahead and pause this video for a minute and take a moment and work out the last one on your own. All right, so let's see what you came up with. So we're doing NH4 to CO3, okay? So we have nitrogen, hydrogen, carbon, and oxygen. So we have 4 elements in this compound, right? So nitrogen has a molar mass, if we look at the periodic table, 14.01 grams per mole, to 2 decimal places. Hydrogen is 1.01 grams per mole. Carbon is 12.01 grams per mole. And oxygen, again, is 16.00 grams per mole. Okay? Now, let's multiply. How many nitrogens we have? Well, there's really a 1 there, right? So what we're going to do is take 2 times 1. That gives me 2. So I'm going to multiply by 2. So I take the 2 and I multiply everything inside the parentheses. So for hydrogen, it's going to be 4 times 2, right? Or 2 times 4. And that should give me 8. I only have 1 carbon, and I have 3 oxygens that I need to multiply by, okay? So let's do that. So this one is 28.02. This one is 8.08. This one stays as 12.01. And then I have 48.00. Okay. So there's those values. Now I just need to add them up. I add them up, I get 96.11 grams per mole. Okay? And that should be my answer. 96.11 grams per mole of, and I probably should state, of ammonia carbonate. That's what the compound is, ammonium carbonate. All right? Awesome. Hopefully you're catching on to this well. All right. All right. Of course, I will give you more practice in class on how to find the molar mass and all of that jazz as we go. Okay. So now what we're going to do is we're going to turn our attention to what is called the mole map. All right. Because now we're going to start actually using some ideas of the mole into some calculations using dimensional analysis, okay? So the mole map is in your study guide. I have it actually over here. Let's see, I'm moving this over so you can see our mole map here, okay? So this mole map should be in your study guide already, okay? So let's use this mole map to solve some problems. So I'm going to kind of talk you through it a little bit using dimensional analysis. So the thing you got to look at is on our mole map is that these boxes, I want you to think of representing islands. Okay, this is a map. Okay, and so this is a map of an island chain. Each island has a specific name to it. This is called the mass island. The mole island. This is the number of atoms, molecules, or the number of anything island, essentially. And this is the volume of a gas island, okay, up here, okay? So we have the mass island, the mole island, the volume of a gas island at STP, which we'll talk about later, and then the island of anything, a number of anything, okay? Number of atoms, number of molecules, number of formula units. That's what we use in chemistry, but it could be crayons, pencils, donuts, whatever, anything, okay? Now, connecting these island chains are these bridges, okay, as you can see from these arrows, all right? Now, these bridges go in both directions, as indicated by the arrows, okay? However, you must use the bridge to cross from one island to another. You cannot skip, like go from mass island to number of anything island at all. You can't do that. The only way that you can get to the number of anything island from the mass island is you have to cross what are called the molar mass bridge to the mole island. And then from the mole island, we're going to cross this bridge, which we're going to call Avogadro's bridge. Okay, and I'll talk about that in a minute. Avogadro's bridge to the island of anything. Okay, so you must cross those bridges. That's how the mole map is going to be laid out and work. Okay, now we talked about Avogadro's bridge here. The reason why I call it Avogadro's bridge is because the number that's 6.02 times 10 to the 23rd, that's equal to 1 mole. This number is often called Avogadro's number, okay? Named after an Italian scientist, Amedeo Avogadro, okay? He did a lot of work when it came to developing the mole theory in time, okay? And so this number is his number, and so therefore we name it after him, Amedeo Avogadro, or Avogadro's number, okay? Not avocado, okay? It's not a fruit, all right? Avogadro, okay? So, okay, so there we are. Now, let's do some problem solving. So in your study guide, there's kind of a section here where we can practice setting up a dimensional analysis problem using the mole map to solve a particular, what we call stoichiometry problem or a mole problem, okay? So let's start with this. Let's say we have a situation where we are given 12.14 grams of water, okay? And what we want to know is how many moles of water, okay? So in other words, it's really a conversion problem here. It's just like we've done earlier when we said, okay, you have this number of grams, how many kilograms do you have, okay? So we're using dimensional analysis again for simple conversions, but in this case, we're using the mole and Avogadro's number and so forth, okay? So I noticed that my initial unit is in mass. That's what I'm given. So that tells me that I'm actually starting over here at the mass island, okay? That's what I initially have. And I need to convert it to the moles, which means that I'm going from the mass island to the mole island, okay? So the bridge that I have to cross in order to go from the mass island to the mole island is using the molar mass, okay? So let's do that, all right? So I'm going to set this up in a normal dimensional analysis situation. So I take my original 2.14 grams of water and I place it over 1, right? There's my pickets. And then I use my conversion factor. Well, what's my conversion factor is the molar mass. It's the bridge. All bridges are conversion factors, okay? Well, how do I know what the molar mass of water is? Well, we calculated it earlier, and we found that the molar mass is 18.02 grams of water. That's equal to 1 mole of water, right? So I have to weigh out 18 grams of water to get it 1 mole. Well, notice that I don't have 18 grams in my original problem, right? So I should have, as a final answer, less than 1 mole, okay? So I'm going to use this molar mass of water as my conversion factor. That's going to go right here in the second bracket, okay? So because mass is here, I'm going to put mass on the bottom. So there are 2 units in the molar mass, right? 2 units, grams and moles. So we got to decide, does the gram unit go at the bottom or the top? Since we're getting rid of grams, the gram unit has to go at the bottom. So I'm going to put 18.02 grams of water at the bottom. Okay, but that's only half of my conversion factor. My other half is the 1 mole. So that's going to go on top, the 1 mole of water. So there, that's my conversion factor. That's my molar mass right there. Okay, this is the molar mass of water. Okay, now if we're dealing with a different substance, this is going to be different molar mass, right? Depending on what material we're looking at. So my mass is canceled out, leaving me with moles. So now I can just do my calculation. I can take 2.14 grams times 1 and divide it by 18.02. No different than what we've done before with dimension analysis and unit conversions. In other words, all we're doing is a unit conversion system. We're not dealing with metric units, we're using mole units essentially. Okay, so let's do that calculation. Let me grab my calculator. And let's take 2.14, divide that by 18.02, and I get, and I need 3 significant figures because I started with 3 significant figures. I'm going to have 0.119 moles of water. And that should be my final answer, 0.119 moles of water. Okay, that's it. Done. Again, I'm using the mole map to help me to do unit conversions, essentially. Okay, just going from island to island and knowing the bridges that I have to cross, which are my conversion factors. Okay, let's try one more. Okay, I'm gonna erase this problem now. Let's do a different one. Let's use a different substance, okay? Let's do something like an element instead of a compound, okay? So let's say I have, let's say I have 0.362 moles of, well, we've been using copper, so let's do copper. Solid copper, so 0.362 moles of copper, and I want to know how many atoms, or in other words, I should say the number of atoms of copper, okay? So ask yourself, where do I start, right? Here's the mole. I'm given the mole, that's the value I'm start with. I'm trying to find the number of atoms. So I'm going to start at the mole island. Where am I trying to get to? The number of, so we're doing the number of anything island right here. So essentially I'm going from moles of copper to number of atoms of copper. Okay, so I'm going this direction. So I'm going to set up my dimensional analysis problem, 0.362 moles of copper, okay, over 1. Running out of board space here. Hopefully you see that, okay. Now, what's going to be my conversion factor? This is what I start with. I need a conversion factor to give me the number of atoms. Well, if I'm going from moles to number of atoms, I'm crossing the Avogadro's bridge. So in this case, I need to use this conversion factor, not the molar mass, because I'm not doing anything with mass. So I'm going to use the Avogadro's bridge. So this is the mole, there's the mole, this is the number of atoms, right? So I'm going to put 1 mole of copper on the bottom. That's this, 1 mole right here. That's that unit there. And then I'm going to put 6.02 times 10 to the 23rd copper atoms. Okay, and I'll just calculate my answer. So remember, moles cancel, leaving me with copper atoms left. Okay. So I'm taking 0.362 and I'm multiplying by 6.02 times 10 to the 23rd. And I get, you can verify this using your own calculator, I get 2.1792 times 10 to the 23rd. But I only can have 3 sig figs, so really it's going to be 2.18 times 10 to the 23rd copper atoms, right? So this right here is my final answer to that problem. I would say that I have 2.18 times 10 to the 23rd copper atoms in 0.362 moles, okay? Again, it's just a simple conversion. It's what I'm really doing. So we've looked at 2 examples. We've looked at a mass to mole conversion. That's the first example. And we've looked at a mole to number of atoms conversion, okay? For the mass to moles, I use the molar mass. Now, if I go backwards from mole to mass, I'm still using that same molar mass bridge. So I must use the molar mass, even from going from moles to mass. Okay? From moles to number of anything, I use Avogadro's bridge, or his number, or back and forth. Either direction, I must use that bridge. Okay? That's kind of what we're trying to get at here. All right? Good? All right, now you have some problems in your study guide to work through. I'm going to erase my board here. Okay, and I'm going to give us some time to work through some of these problems that are in your study guide. Okay, so I'm looking at my study guide here. I'm turning to problem number 1. Okay, so just got my study guide. I'm looking at problem number 1. So it says use dimensional analysis and the mole map to solve the following problems. Okay, I know you can't see the mole map right now, but you do have the mole map or a copy of it in your notes so you can follow along. Okay, so number 1, it says calculate the number of moles. What are we supposed to calculate? The number of moles there would be in each of the following. Okay, so A, 30.0 grams of calcium carbonate. Okay, limestone. Okay, calcium carbonate. So what I'm going to do is I'm going to look at my problem here. This is number 1. And I'm going to look at what I'm given is 30.0 grams of calcium carbonate. And what are they asking me to find? I'm doing a conversion here. So what are they asking me to find? Well, they're asking me to find the number of moles. The moles of calcium carbonate. Okay? So I need to go from grams to moles. Okay? Now I set that up like that so I can keep that mentally in my mind what I'm trying to solve for here, which is the number of moles given the mass. Okay? So I need to go from mass island to mole island. Very similar to the first example that I gave you with water. Okay? So to do that, I'm going to set up my dimensional analysis problem of going 30.0 grams of calcium carbonate over 1. Okay? Now, my next bracket must be my bridge. My bridge. What bridge am I going to cross if I'm going from mass to moles? Well, I'm using the molar mass bridge. So what goes in here is the molar mass. The molar mass of what? The molar mass of calcium carbonate. Okay? So that means that you have to calculate this molar mass. You have to use your skills using the periodic table when I showed you how to find that molar mass. Okay? So I'm going to speed things along here, but if I was you, I would take the time to make sure that you can calculate this. Okay? So I found that the molar mass of that is 100.909 grams of calcium carbonate is equal to 1 mole. Okay? That's the molar mass. So that should be going right here. Well, grams should go on the bottom. So 100.09 grams of calcium carbonate and 1 mole of calcium carbonate on top. Now notice I am using the term, the correct, not only the units, but also the compound that I'm putting in there in the bracket so I can keep track of things as we get more complex stoichiometry problems. Okay? So my grams cancel out, leaving me with moles. So all I do is divide these two, essentially, right? So use your calculator, you can divide, but I essentially got 0.300 moles, okay? Three significant figures of calcium carbonate, okay? And that's my final answer for number 1, okay? Not too bad, hopefully. All right, let's run to number 2. Number 2, we're giving the mass again, so it's very similar to number 1. We're given the mass and we're trying to find, it looks like, the number of moles. So I have 125 grams of vinegar, which is CH3COOH, and I need to find the number of moles. Okay? The number of moles, I don't know. Okay? So I'm going to set this up. 125 grams of CH3COOH over 1. And I need my conversion factor. Again, I'm going from mass to moles, so I need my molar mass. That's my bridge I'm crossing. So you would have to calculate that. I calculated the molar mass of vinegar of 60.06 grams per mole. Okay? So this is the molar mass of vinegar, okay? So again, I'm going to put my mass at the bottom of CH3COOH to 1 mole on top of CH3COOH, okay? And then I just solve. Grams cancel, leaving me with moles, and I get 2.08 moles of CH3COOH. And that becomes my final answer. Okay? Just like that. Okay, good? All right. All right, hopefully you're catching up with us. Okay, let's do 2A together. 2A, it says calculate the mass given 4.5 moles. So now we have the moles, 4.5 moles of NH3, and now we're trying to find the mass. We're going in the opposite direction. We're going the other way now. We're going from moles to mass, but we still use the same conversion factor, molar mass. Okay, so 4.5 moles of NH3 over 1. Okay, what's the molar mass of ammonia? Well, calculate it. Okay, I did it, and I found it to be 17.04 grams of NH3 is equal to 1 mole. Okay, that's the molar mass of ammonia. So now the mass has to go on the top, and 1 mole goes on the bottom. Notice that the mole and the mole match. They're diagonal of each other, so they can eliminate. So that means the 17.04 grams of ammonia goes on top. Okay, moles go away, and we have our final setup. And now I multiply, and I get 77. Do better than that. 77 grams of NH3. Okay, and that's my final answer. Cool. All right. Now, what I want you to do is do the next one on your own. So pause this and work out the next one. Okay. Go ahead and do that. All right. You should have worked out 2B. You should have gotten an answer of 461 grams. Okay. 461 grams would be the answer to that. Now, I'll set it up really quick to show you. So I have 2.56 moles over 1, and then I have 1 mole, 108.18 grams, and that gives me 461 grams. So that's how I set that problem up and solve for it. Okay, just check your work on that. All right, let's do number 3 together. So number 3 asks you to calculate the number of copper atoms in 1.21 moles. So 1.2 moles of copper, this is very similar to what we did as an example problem, is equal to the number of copper atoms. Okay? So now we're going from moles to number of anything island, okay, essentially. So 1.2 moles of copper over 1, and we need to go from moles to the number of anything, so we cross the Avogadro's bridge now. The Avogadro's bridge. So that means Avogadro is 6.02 times 10 to the 23rd, there's this number, equal to 1 mole. That's the bridge that we're taking. So we know that 1 mole on the bottom of copper, okay, moles to moles, right? Then Avogadro's number on top, that's copper atoms. So I get rid of my moles. So I take 1.2 times Avogadro's number, and I get 7.2 times 10 to the 23rd copper atoms. And that's my end result right there. That's my answer. All right? That's how you solve it. All right, go to number 4. I want you to pause this video, and I want you to do number 4 by yourself, okay? Number 4 by yourself. All right, you should have had some time to work out number 4. I get an answer of 9.0 times 10 to the 23rd. That's gold atoms. Okay, gold atoms. So there you go. So check your answer to mine. If it's not the same answer, then come to class and we'll discuss that. Okay. All right. I need to move on. Let's go to our next problem. All right. Let's go to number 5. We'll do number 5 together. All right. So number 5 says calculate the number of molecules, the number of, right? That sounds like the number of anything island. Calculate the number of molecules of CO2 in a fire extinguisher that contains 1,000 grams of CO2. So essentially we have 1,000 grams of CO2, carbon dioxide. And we're trying to find the number of molecules of carbon dioxide, okay? So on our mole map, ooh, wait a minute. We cannot go from mass to the island of anything directly, right? There's no bridge. So how do I get from mass to the island of the number of anything? Well, I have to go through the mole first, right? So I have to go from mass to the mole island, and then from the mole island down to the number of anything island. So I have to do multiple steps here, okay? So 1,000 grams is how I'd set up 1,000 grams of CO2 over 1, my normal brackets. Now I'm going to go to my mole island. So to go from mass to mole island, I need the molar mass of CO2. Well, I calculated the molar mass of CO2 to be 44.01 grams. CO2 equals 1 mole. Okay, so you're gonna have to calculate that, all right, using the periodic table, your molar mass. So that means my grams go at the bottom, 44.01 grams of CO2 to 1 mole of CO2. That cancels out the grams. So that allows me, if I did this calculation right now, I would be in moles, and I would be at the mole island. But I don't want to stay at the mole island, right? That's just a stepping stone to get to the real island that I'm trying to get to, which is the island of anything, okay? Number of anything, really. So I need to go one more step. I need to cross one more bridge. So here's my molar mass bridge, okay? Molar mass, but now I need to cross the Avogadro's bridge, all right? And so I need to use 6.02 times 10 to the 23rd. CO2 is equal to 1 mole of CO2, okay? So I'm going to put my 1 mole of CO2 on the bottom, 1 mole, and my Avogadro's number 6.02 times 10 to the 23rd on top. And then I do my calculation. Notice the moles and the mass cancel out, leaving me with molecules of CO2, all right? Now, my final answer should be 1.368 times 10 to the 25 CO2 molecules. Okay, there's my answer. Wow, I had to go multiple steps here. Just like you've done in other conversion problems early in the year, you had to do multiple steps in dimensional analysis, okay? Same thing here when you're dealing with stoichiometry or molar conversions, okay? We needed to move from the mass island to the mole island to the island of everything. And to do that, we had to cross the molar mass bridge, which we did here, which we calculated for carbon dioxide. Then we moved over the Avogadro's bridge in order to get to the island of number of anything, okay? So that's essentially what we did here, okay? Hopefully this makes sense to you, right? So what I want you to do right now is just pause the video, and I want you to work out the remaining problems, okay? I'm gonna list the answers to those problems right here, okay? I'm not gonna work them out. I'm just gonna put the answers, and I want you to see if you, after working through those, that your answers meet mine. So here would be the final answer. So for number 6, the final answer would be 1.84 times 10 to the 23rd NaClO3. Number 7 is 26.6 grams copper. Number 8 is 60.0 NaOH. Number 9 is 5.41 times 10 to the 23rd atoms of atoms in H2O. Okay. Now this one right there is a tricky problem. I'm interested to see if you can get number 9. Okay. So be careful on number 9. If you can't get this number, all right, come to class and we'll talk about it, okay? But try it, Number 10, the answer should be 5.38 times 10 to the 24 atoms in C12H22O12. This one too. These two right here, number 9 and 10, are very similar in solving those problems. So see what you can do with 9 and 10. You may have to come and ask some questions about that, but that's fine. Okay. So that's it for this part 1 of lesson 8, the mole, in your study guide. We will just watch the second video in order to get essentially the rest of this lesson. Okay, so that's it for right now. Good luck, practice, go back. I promise you, if you go back and rethink all of these example problems, rework them, you'll be better for you. You'll be better off. Stoichiometry, this is what this is called that we're doing, which is these molar conversions. Stoichiometry is really an important topic in chemistry, and we're going to be using molar conversions quite a bit throughout the year. So that's why we're starting off now early, so that we have plenty of time to practice and then apply it to situations that are coming up. Okay, that's it for today. We'll see ya.